Welcome back, ladies and gentlemen, to another episode of Dave Does Math from Home. Today we are wrapping up Calc 1. It's time for section 5.3. This is the end of Calc 1. After this, no more sections to Calc 1. I'm sure I'll see you again in Calc 2, where we'll pick up right where we're leaving. We'll pick up right where we're leaving off. But this is it for Calc 1, so that's exciting. You made it. You got here. Calc 1 ends on, it ends strong. It ends on something called the fundamental theorem of calculus, which is a really big deal. And it's about areas. We're back in chapter 5. We're doing areas under curves. I promised for a while that we would come up with a technique to very precisely determine the exact areas under curves, even if they don't have nice geometric formulas to tell us the area. And today we do that. First, I'm going to start with a pretty standard looking function. Let's do f of x equals x plus 2. That function looks like this. We'll say this is 6, maybe? This is 4 comma 6. I don't need it to be 4 6. It can be anything you want. Okay. So the question is, I want to know how much area is under f of x between 0 and, let's say, b. B seems like a good bound. B for bound. We'll do that. Whatever b is, I think you'll agree that we can find the area by splitting this into a rectangle and a triangle. The rectangle should have area 2 times b. It's got a height of 2 and a width of b. B is the amount of space between 0 and b. So this rectangle on the bottom is 2b. And the triangle, this triangle should be, it's a width of b, it should have a height of b, so this triangle should be 1/2 b squared. Not so bad. We can use geometry. No matter what b is, however far out you want to push b, you'll get 2b area from the rectangle, and you'll get 1/2 b squared area for this. So the area is 1/2 b squared plus 2b. Here's where this gets really weird. The antiderivative of f of x dx is 1/2 x squared plus 2x plus c. These are the same. The last video ended pretty abruptly. I didn't get to explain why antiderivatives and definite integrals use the exact same symbol. They both use this big curvy s symbol and a dx in the back end. The reason they both use these same symbols is because they both mean the same thing. The antiderivative of a function will give you the area below that function between 0 and your bounds. If you want to go from a different bound that's not 0, you can go from a to b and then subtract them. So if you wanted to, the area under f between 0 and b is this. Let me just draw a different picture. let's do the same thing. If I put A here and B here, the area between 0 and B is this. The area between 0 and A is this. And this area that we actually want is what happens when you do the area from 0 to B minus the area from 0 to A. And we know the area from 0 to B is 1/2 B squared plus 2B. And we know the area from 0 to A is 1/2 A squared minus 2A. Both of these things are the antiderivative evaluated at these two bounds. And that's the beauty of calculus. That's the big reveal at the end. The huge M. Night Shyamalan, the plot twist. We can find exact areas beneath curves by taking antiderivatives, evaluating them at the starting point and the ending point, and subtracting those two things. The one quick little side note here is, I feel like this is important to mention because I made a big deal out of this in the last video, in the 4.9 video. I said every time we do an antiderivative we need to add a plus c. And that's mostly true. Except when we're doing these definite integrals. If you add a plus c here and you add a plus c here and then you subtract this from this, the c's just instantly cancel. So you don't have to add them when you're doing areas. If you're doing definite integrals by calculating antiderivatives and subtracting those things, you don't have to include the c's in those particular antiderivatives because they will cancel. Which I think is really cool. It's time to put the fundamental theorem of calculus to work. In our videos on section 5.1, we spent a lot of time I'm just going to pause right in the middle of that thought to clear the board. In our videos on section 5.1, we spent a lot of time working with this function x squared plus 1 on the interval from 0 to 6. And we got some increasingly accurate estimations for the area under this curve. I'm coming back to this because now we have the possibility to find the exact area under this curve, and I want to do it. The exact area under this curve, also known as the definite integral from 0 to 6 of x squared plus 1 dx. This is the notation for the exact area under the curve. It's no coincidence that it uses the same symbol as an antiderivative, because we're going to do this by finding an antiderivative, which should be x cubed over 3 plus x. This is the antiderivative. I'm not worried about the c. I can get the exact area by evaluating this at 0, evaluating it at 6, and subtracting those two numbers. That's what this bar means. The big bar, big vertical bar on the right of a expression means evaluate it at this number and evaluate it at this number and subtract those results. So this means 6 cubed over 3 plus 6, that's evaluating at 6, minus 0 cubed over 3 plus 0, that's evaluating at 0. The result of this calculation should give me the exact area. I think our estimations, I'm just remembering what I did days ago. I think the first The first approximation we did with only 3 rectangles, our left-hand sum was 46 and our right-hand sum was 118, and we averaged them and we said it should be around 82. And then I think we did it again with 6 rectangles, and I don't remember what the upper bounds and the lower bounds were, but we averaged them and we got 79, and we said we were glad that it was lower than 82 because we expect increased. We knew that 82 was an overestimate because this function is concave up, and so we were glad that our estimate became lower as we expected it to become more accurate. So those are the numbers that we thought were close. 82 was our first guess, 79 was our second guess. Let's see what we actually get here. This is going to be 216 over 3 plus 6 minus 0. 216 over 3 is going to be 72 plus 6. 78 is the exact area below this curve between 0 and 6. So we were really close. 79 was within 2% accuracy. Closer to 1% accuracy. That's pretty well done. Have you ever wondered how much area is beneath a sine wave between 0 and pi? I definitely have, but now we can know for sure. The area from 0 to pi beneath sine of x dx can be calculated by finding an antiderivative of sine x, which is negative cosine x. Again, don't have to worry about the plus c because it's a definite integral with bounds. If I didn't have these numbers here, then it would be asking for an antiderivative, and I do need those plus c's. But here, definite integrals, no c's necessary. The antiderivative is cosine. I'll evaluate that at 0 and pi, which still means I evaluate negative cosine of pi minus negative cosine of 0. Cosine of pi is negative 1. Make that negative again, you get positive 1 minus negative 1. The area underneath the first hump of a sine wave is exactly 2. I think this is amazing. Intuitively, antiderivatives and area shouldn't be related, but they are. Intuitively, they should be related. It's just not something that you think about. There is a very compelling geometric proof for why they are related, and I would be happy to go over that if you want me to in class. Ask about it. It's a very fun exercise. It's just not something I think we should put in the video right now. I want to do more examples. I want to know how much area is below a square root graph between x equals 1 and x equals 9. So I'm going to do the definite integral from 1 to 9 of square root x dx. And I can find this by taking an antiderivative of root x and then evaluating it. The antiderivative of root x from the last video, hopefully you remember, is 2/3 x to the 3/2. And I'm evaluating this at 1 and at 9. So this will be 2/3 9 to the 3/2 minus 2/3 of 1 to the 3/2. 9 to the 3/2, to the 3/2 means take a square root and then cube it. So 9 to the 3 halves, the square root would be 3, cubed is 27, 2/3 of 27 is 18. Minus 1 to the 3 halves is just 1, so it's 18 minus 2/3, and you get 17 1/3. That's this area. Now you know. Now you know exactly how much area is underneath a square root graph. This is kind of a big deal. It's enough of a big deal that we're going to spend pretty much all of Calc 2 talking about it. First we're going to experiment with a technique for taking antiderivatives of slightly more advanced functions. It's sort of like doing the chain rule backwards so that we can handle composite functions. It's pretty exciting. Once we have that figured out, we're going to spend a while doing applications of this. Turns out being able to find the area underneath curves or between two curves is very important. And we can do other things with this idea, like we could take this shape and spin it around the x-axis to generate this solid of revolution. And we can find the volume of those. We'll spend a while doing that in Calc 2. Then we'll come back to integration techniques, so we can learn about how to take the integrals of even more complicated functions. Right now we're stuck in pretty basic functions. We can do like basic power rule stuff, basic trig stuff. When functions start combining with each other in function composition or function excuse me, function composition or function products, things are going to get really messy really fast. Like the product rule for derivatives is there's a lot of pieces, but it's pretty straightforward. The product rule for integrals, when you're trying to do that backwards, is a horrifying mess, but it's very doable. So we'll do that. There is a lot of Calc 2 dedicated to exploring this idea in incredible depth. I'm looking forward to doing that with you soon. Stay tuned. This is Dave signing out for Calc 1.